This is the 24th video in a class on single agent search. And in this video, we're going to continue where we left off in the last video, but we're going to be looking at some of the mathematical pieces behind computing pattern databases. And so the idea here is that we are going to take an abstract state space. And so we have an initial state space S, and we've mapped it to an abstract state space S, or capital S, phi of S, sorry, using a domain abstraction, which means we've taken some of the pieces of that state space and we've abstracted them away. And then what we're going to do is we're going to do a breadth first search from the goal in phi of S to compute distances in the abstract state space, abstract distances to the goal. And I thought I would start this just really quickly. I know my video here is a little bit small, but just an example of this. So this is obviously the Rubik's Cube. And what you see in Rubik's Cube is that we have a 3x3 cube. And if you look at the cube, we can distinguish between the corner cubies, which are have 3 different colors on them, and then the edge cubies, which have 2 different colors on them. And we'll be talking more about Rubik's Cube in a couple more videos. But if we look at Rubik's Cube, because I did bring this up in one of the previous lectures, how would we abstract Rubik's Cube? It ends up that actually the 2x2 Rubik's Cube is an abstraction of the 3x3 Rubik's Cube. And what's going on here is the 2x2 Rubik's Cube gives us all of the corners, all the corner cubies, and it essentially abstracts away all the edge cubies. And so if you know a solution to the 2x2 Rubik's Cube, then you could use that solution for solving as a guide for solving the 3x3, because in order to solve the 3x3 Rubik's Cube, you must actually get all the corners into their correct locations. And so this is just an example of an abstraction function. And the idea is then, well, as long as I can do a breadth first search from the goal backwards through the whole 2x2 state space, and there's only 88 million states there, then I actually can get a pretty good heuristic for the full 3x3 Rubik's Cube. And so that makes sense, hopefully, as a high level idea. And we looked at the sliding tile puzzle, again, as a high level idea that makes sense. But I want to get into some of the gory details of what actually goes on here. And in particular, when we're building pattern databases like this, we don't typically actually build our abstract state spaces. We typically actually stay in our regular state space, but we use something called a ranking function. And a ranking function is a function that maps a state. So it's mapping a state into an integer. And this is a form of a perfect hash function. And so the idea is we're going to get a one-to-one mapping between states and these integers that are giving me, in practice, they just give me an index in memory. And so just to show here, like the idea would be is that I have some state space. Well, in fact, let's look at this. Let's be precise here. So this is basically a perfect hash function. The ranking function is sort of the mathematical name for this, but we also care about unranking functions, or we can care about unranking functions. It depends on how you're implementing things. There's ways that we can implement this where we only need a ranking function in some state spaces, particularly large spaces. And again, when we think about, when I talked about breadth first searches and this idea that we have this ability to go back and forth, when we did external memory searches between states with its implicit representation, this is where we're getting these low-level details of how you actually can do this process of getting states to these integers. So we could look at a couple possibilities here. So we could think, for instance, like a 2D map. And we could have a 2D map with some obstacles in it that are blocking the world in different ways. So maybe these are places that I can and can't travel inside the map. And so this gives me a limit of where I can and can't go. And here it's very hard to represent, if we think about trying to represent the obstacles versus the non-obstacles. So with a map like this, typically what we're doing is we have some width. And then what we have is I've got an XY coordinate. And if I want to be able to represent this, we assume there's ways you can get around this, but let's just assume that we need to represent sort of all possible locations that are within the size of the grid. And so if I want a function here, what I want is I want an xy coordinate. So that's my state, and I want to be able to map that to a unique integer. And the way we generally do this, so and that you can do this based on the height or the width, which may matter for caching purposes, because you want to be careful about going through cache lines in the right order. I'm not going to talk about that low level of detail here, but it's something to be aware of. So we think about an xy coordinate. If I placed it somewhere on the screen, what I realize is that for y, so for instance, for every y coordinate here, we know that we've used up a bunch of entries that are exactly the width of the map. So an xy coordinate, I can basically say, look, take y times the width of the map plus x. And because this will give me an integer coming back from this. And because I know for every y coordinate, so if I start at 0, then this tells me sort of how many entries I've used so far. And then plus x tells me the entry that I'm at this current point in time. So if I give an xy, I do y times width plus x, and that'll give me a function that is basically a perfect hash function, in that it's a perfect hash function for converting a two-dimensional array into a one-dimensional array. It still won't represent the fact that some places are obstacles and we can't go there. And there's not necessarily a good way to always be able to do that in a 2D map, because we can sort of have arbitrary obstacles here. But in state spaces that are more like permutations, then we can do this a little bit more easily. And so we see that for the Rubik's Cube, we see it for the sliding tile puzzle, we see it for Towers of Hanoi. And I'm just going to we'll do the Towers of Hanoi here really quickly to talk about how we can do a hash function. And then we're going to look at permutation problems, because those are a little bit more complicated. There's also problems that are combinations, and this would be like, if you think about the single agent problem in Chinese checkers of trying to move your pieces across the board as quickly as possible, that's the pieces, because they're not distinguished from each other, that's combinations there. But I'm not going to, in this talk, I'm not going to talk about that. But there's some really nice algorithms you can use there that are very efficient to be able to compute ranking and unranking. And the key is that in many problems that we're doing, like doing a large breadth first search for a pattern database, most of the time is actually spent in these operations where we're trying to take a state and convert it to an integer, or optionally, depending on my implementation, taking an integer and mapping it back to a state. Okay, so that was the 2D map is over here, and for a 2D map, there's our 2D map. We just do y times width plus x, and if your map is arranged in the right way, this will also give you cache efficiency. If we look at Towers of Hanoi, so I'll just put TOH here, and we're going to look at the 4-peg Towers of Hanoi, because it'll make the math work out really well. And we're going to have some number of disks here. And so for simplicity, let's just say that we're going to have 4 disks here. And I'll put them here. So this is Towers of Hanoi. And the goal is to get the pegs on the other side. And very interestingly, I think it was 2 lectures ago or 2 videos ago, I showed this picture of Towers of Hanoi and talked about the structure of the state space. If we think about a domain abstraction that I might use for Towers of Hanoi, basically what I can do is just get rid of some of these disks. If I get rid of some of the disks, I have a smaller state space. And when I do that, I can just solve that smaller state space. And I can use that. And actually, there's some nice tricks you can do along with that to get a heuristic. Towers of Hanoi also has some really, really interesting properties that make compression of heuristics very, very efficient. But I'm not going to talk about that here in this lecture. Okay, so we think about it here, though. In this case, we have 4 disks that we want to represent. And each of the disks can be on each of the 4 pegs. And so what I can do is I can basically represent my state here as 4 pieces here, or 4 slots of memory. And each memory, I'm going to represent where a particular disk is. And just for convention, I can make the first one be the largest, but it could be the smallest. There's not really a big difference here. And because there's 4 possibilities here, in binary, I can do that using 2 numbers. So if I label these 0, 1, 2, 3, then obviously that's 0, 0, 1, 1, 0, 1, 1. But then what I can think about here is if I want to represent this state, then the first disk is in location 0, the second disk is in location 0, the third disk is in location 0, and the fourth disk is in location 0. And so this gives me an exact mapping between a state and an integer, where this is 2 bits. So each of these is 2 bits. And so overall, this would be an 8-bit number, which would be 0, and 0 would represent this state. But I could do something like this. And I can just write anything down that I want here, 3, 1, 1, 0. And what is this going to represent? So I'm going to draw this out. I haven't thought about what this is ahead of time, but I've got 0, 1, 2, 3 here. And it just says, well, my biggest disk is on peg 3. And then my next one is going to be on peg 1. My next one is going to be on peg 1. And my last one is on peg 0. Okay, so there's a one-to-one mapping in this representation between this, which is a number here. So I'll write it out in binary. So right in binary, this is 1, 1, 0, 1, 0, 1, 0, 0. And every possible 8-bit combination here represents exactly one state. And obviously one state directly maps to an 8-bit representation. And all of them are legal and all of them are valid. And so what that means is for Towers of Hanoi, it's very simple to get to this representation here. And when I want to do a breadth first search, what I'm going to do is actually I'm going to, now Towers of Hanoi, the implementation here is a little bit different than in other state spaces. But essentially when I'm solving this problem, what I'm going to do is I'm going to take a particular state that I'm in. I'm going to look at the operators that are applied. I get to some other state, and then I just, for instance, there may be 10 disks here, but I'm just going to look at the top 4. I don't actually have, I could leave the 10 disks, all 10 disks there. But when I do the ranking, I'm just going to look at the locations of the top 4, and I'm going to put them into bits like this. And then from that bit, I'll get a unique integer. And then that's the location in memory that would store the distance from this state to the goal. Okay. And so the idea here, let me just write what the breadth first search looks like. So if I write down the breadth first search, then we'll see, I'm going to write the generic PDB building sort of the overview of how this works. And then we're going to go back and look at how we can build a ranking function for something like the sliding tile puzzle. Okay, so what we're going to do is we're going to do a breadth first search in S, the original state space. So I don't have to implement like the abstract state space directly. But what we're going to do is when I want to write a state down, so I'm going to actually be writing the depths in the abstract state. So basically what I'm going to do is mark phi of the start as 0, depth 0, that's my start. And then what am I going to do? And now there's a couple different implementations that I can use to do this. One thing that I can do is I could have a queue that is going to store states. And so if I have a queue, then I'm marking this, and then I'm going to put start on the queue. Okay, but there's many different algorithms that I actually can use for building the pattern database. I'm going to talk about a breadth first search right here, where we're going to maintain an explicit queue. If you go back to the lecture on external memory search, we talked about in that lecture how we could use we don't have to maintain a queue. We actually can use the memory that is being used in this case, for a pattern database, can be used directly as your queue. But that does require an unranking function, and I'm not going to talk about that today, or I won't talk about it too much. But there's other algorithms you could use. So you could use like even a depth first iterative deepening search and other things like this. So I'm going to put the start on the queue. And then I'm going to say, while the queue is not empty, okay, so we want this to be a queue where we're putting items in the back and we're taking them out of the front. And so that means that we're going to get them in order according to their depth. So we're going to generate states and put them in the back, and then we're going to pull them out of the front. Okay, and so we're going to mark the start as 0. And while the queue is not empty, so we're going to pop the front, or remove the front. It's not a stack, so I'm not really popping, but I remove the front. And then what I'm going to do is for each successor, and these are successors in the regular state space. What I'm generally going to do is, and I'm going to, this is a little bit, I'm going to write it in a simple way in the pseudocode, but basically what we want is we want to store the depth, sorry, and remove, that's, we're going to remove n from the front here. So store the depth of phi of n plus 1 in the location phi of s. Okay, and then only if, so if the depth is already stored there, then we're not going to store it. And if this was a new value, was new, then we're going to add s to the queue, to the back of the queue. Okay, so what's going on here is I've got this queue. I take my first state out the front. I look at all the successors in the actual state space, and then I take the depth of the parent plus 1. We're assuming unit costs here. And then I abstract each of the children. And if I go to the child and there's already a value there, then I'm just going to discard it. Otherwise, I'm going to say store. So I'm not necessarily saying this perfectly in the pseudocode, but I'm going to store it if it hasn't been stored already. And if the value was new, then this is a new state. And I haven't seen it before. I haven't seen phi of s before. So I'm going to put s into the queue. Okay, so we're going to do that. And basically, this is all we do. And when we're done with this, we'll have computed the breadth first search. Okay, so this isn't very hard, and it doesn't require much more than we've done. We just need to have a phi function that takes a state and does this mapping that says, you know, here's a state. Now give me basically a location in memory where I can store all these depths. And what I have in the end is sitting in memory here. So this is like in main memory or an array. I just basically have a big table here, you know, 3, 4, 2, 1, 7, 0, 5, 2. And this is just, that's my heuristic, is this big table of values that I get by doing this breadth first search in the abstract state space. I'm using actual states, but I'm using the abstraction function for actually writing the states down here into main memory and mapping to where they go in main memory. Okay, so that gives us our general process, and what we want to look at is how do we actually do this for something like the sliding tile puzzle. And the real thing here is ideally this is compact. Like ideally every single entry is being used. If we were doing something for a 2D map, then we wouldn't necessarily be compact because we've got these obstacles here and we'd have these spaces where I can't actually reach the obstacles, and so there'd be some uninitialized value there. But for other state spaces, we can do that. And let's look at permutations here. And so what we can think about here is we could think about something, if we look at what's going on here. So in this example, we're basically allocating a fixed number of bits for every entry. And so if we think about a sliding tile puzzle, if you remember, like so if I have 9 values, then that means there's 9 factorial orders. But I could think of this as, well, okay, let's just say I have some ordering here. Maybe I have, 7, 4, I'm just, 1, 5, 3. This really doesn't, 0, 6, 2, 8. So I just have some random ordering here. And I could think of basically saying, well, if I have 9 values here, and so I have 9 values, how many bits do I need per value? Well, I can't do it in 3 values. I actually need 4 bits. So we could think about, like, let's say 4 bits per entry, and we could just be putting 4 bits, 4 bits, 4 bits, 4 bits, and we'd represent 7, 4, 1, 5, and so on. But if we look at this, what we're going to have overall is we have 9 values times 4 bits each is equal to 36 bits. And I don't remember 2 to the 36 off the top of my head, but 2 to the 36 is going to be about 70 million entries. Okay, so 2 to the 30th is about 1,000,000, and so and then 2 to the 6th is 64, so that's about 64 million. It's actually around 70 million in practice. And okay, so I'm going to have about 70 million entries, but 9 factorial orderings is the actual number we can get, which is 362,880. Okay, so if we do some representation here where we have 4 bits per entry, instead of getting 362,000 entries, we actually get 70 million. And so we're off by a factor of not 10, not 100, but actually 200. We'd be about 200 times larger than we needed to in the amount of memory we're using. So this seems like a really bad idea. Just write that here, that's a bad idea. Okay, we don't want to do this. So what we have to realize here is when we have permutation, what's actually going on here is that we have a representation, or we want to get into a representation that is a little bit more, well, that is actually representing what's going on. And what's going on here actually is that once I've put a 7 in the world, I actually know that there can't be another 7 here. And so given that there's a 7, the rest of the numbers here are, there's fewer combinations because I know the 7 can't show up. Where inside a representation here with 4 bits per state, I could have a 7, 7, 7, 7, 7. Like that'd be a perfectly valid representation that I could put here, and that wouldn't correspond to a legal state in the state space. So what we need to do is we need something called a mixed radix representation. Okay, and what a mixed radix representation is doing is it's actually going to say, I know that the numbers that I have are not all the same base. So this is treating them like they're all, these are all base 4, because we can get all these values, up to, not base 4, but all base, well, I have 9 values, so base 9. And so you can think about, we have 0 to 8, this is base 9, and then I'm just trying to represent that, even if I use fewer bits to try and represent as base 9, I'm still going to get in trouble here because I actually don't have each of these individual numbers represented as base 9. Okay, so mixed radix representation is actually saying, look, I'm going to write this down. I'm going to write down both the number, and I'm going to write down the, along with the number, I'm going to write down the base of that particular number. So what I have here, if I'm trying to take this array and turn it into a mixed radix representation, what I have is I have 7, and 7 is in base 9. Okay, but at this point, now the rest of the numbers, I want to write them in base 8. And when I want to write them in base 8, well, what we'll see here is, so I'm going to do this conversion one step at a time. 4 is perfectly fine in base 8, 1 is fine in base 8, 5, 3 can both be in base 8, 0 can be in base 8, 6, 2, but 8 can't be in base 8. So what I have to do is say, well, there is no 7. So when I think about this, the 8 actually has to become a 7 if I want to represent it in base 8. And if you think about like the range of values, well, there is no 7. So 8 is really just the maximum value. Okay. So now I'm going to continue this process. So I've got 7 in base 9, and I have 4 in base 8, and I want to write everything else in base 7. So this gives me 1 base 7. Now 5, what's going to happen is because I've taken the 4 out, essentially everything above the 4 gets its value reduced when we move it to base 7. So my 5 is going to become a 4 base 7. My 3 stays a 3 base 7, as does my 0. But my 6 is going to become a 5. My 2 is going to stay a 2, and my 7 is going to become a 6 base 7. Okay. Now, So at this point, we actually have our first three numbers are base 8, 9, 8, and 7. And so now I want to take the next number here and I want to convert it to base 6, or the remaining numbers here. So now I have 4 base 6, 3 base 6, 0, 5 base 6. Oh, sorry. 5 is larger. I have to be careful. Okay, sorry. Let me start this over. What did I just remove? I removed the 1. Anything larger than the 1 is going to be reduced here. My 4 is going to become a 3. My 3 is going to become a 2. My 0 stays a 0. My 5 becomes a 4. My 2 becomes a 1. And my 6 becomes a 5. And notice here, we have 0, 1, 2, 3, 4, 5. So we still have a permutation of these elements, of the remaining 6 elements, as I move it to the next base. Okay, so going down, I want to get now into base 5. So I've got 3 base 6, so I'm going to get 2 base 5, 0 base 5. My 4 is going to become a 3 base 5. My 1 stays a 1, and my 5 is going to become a 4 base 5. Again, I have 0, 1, 2, 3, 4. And I can continue this process. I'm not going to do it just for the sake of time here. But the idea here is that if I can, what I want to do is I want to convert this number. Well, maybe I'll just do it here really quickly without saying everything as I do it, because I'll want to get the final number here. So I've got 2 base 5, so that's 3 base 6, 2 base 5. And now I want to have it a 0 base 4, 2 base 4, 1 base 4, and 3 base 4. And now I want to get 2 base 3. Sorry, my 2 is going to become, so I'm keeping the 0 here, so my 2 is going to become a 1, my 1 is going to become a 0, and my 3 is going to become a 2. And then I'm keeping the 1, so I get 0 base 2 and 1 base 2. And then I'm always going to end up, I'm going to go to base 1, so I actually can only get a 0 here. So this value that I had up here, if I convert it to a mixed radix representation, what I'm going to get is 7, 4, 1, 3, 2, 0, 1, 0, 0, where the base here is 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. And now if I look at this, if I want to do a ranking on here, a ranking is very easy to do once I've converted to a mixed radix representation, because a ranking now says I'm going to have 7. And what I think about is how many values are there for the remaining values here? And the answer is 8 factorial. So I do 7 times 8 factorial, plus 4 times 7 factorial, plus 1 times 6 factorial, plus 3 times 5 factorial, and so on. And if I compute this, this is going to give me a 1-to-1 mapping from, by multiplying by factorials here, I'm going to get a mapping from this mixed radix to what I'm get in the end here is an integer. And by just doing modulo, so all of these values here cannot sum up to more than 8 factorial. And so if I divide by 8 factorial, I'll actually get the 7 back. And if I mod by 8 factorial, I'll get back all of these numbers here. So what I can do, and this is the same thing we do in, with regular integer arithmetic, or when we're thinking about like, base 2 or any other conversion or hexadecimal. This is the type of thing we do when we're converting values or wanting to put like sequence of numbers into bits. This is the type of process that we're doing. And so here we're doing it in a way that allows us to convert this state directly to an integer, and I can get uniquely from this integer back. Now, this requires that I go to a mixed radix representation. And the question is, what is the complexity of getting to the mixed radix representation? And the answer is, if you look at this, so if I was trying to do this in array in memory or something like this, I'm going to take my 7 and I'm going to say, well, that 7 becomes 7 base 9, and I would convert everything else to base 8. I have to actually go through all these values, and I have to take everything that's greater than 7, and I have to, or greater than or equal to 7, and I have to reduce it. Okay. yeah, so I reduce it. So I drew my line over here. So my 8 became a 7. And when I did the 4, I had to go through here and I had to reduce all the values after that. So it ends up to do this every time I pull my first number that in this case, it's basically in base 10. When I pull off some next number and add it to my sequence of values here, I have to convert the rest of the numbers. And so if I have n numbers in my n numbers in the sequence that I'm trying to convert, then the runtime is O of n squared. Because it's 1 plus 2 plus 3 plus 4 plus 5 all the way up to n, which is n times n plus 1 over 2. So that's bounded by n squared. Okay, so we can take something like a permutation. We can convert it from base 10, so there's a complete base 10 representation, to a mixed radix representation. If we convert it to a mixed radix representation, which is here, then it's very simple to convert from mixed radix into an actual equation that would give us a ranking that is a unique integer that represents the state, and we can very easily go from this state back to this mixed radix implementation, a representation. But getting from the mixed radix representation into something more akin to this, which is our base 10 representation, has this n squared overhead. And just to be, so if we're implementing something like this, there's sort of like two pieces we need to understand for doing a pattern database for something like the sliding tile puzzle. One we need to understand is that I need to do this conversion to a mixed radix representation, because this is allowing me to get unique representation in memory. Basically, I'm going to get a compact, my pattern database is going to be compact. Every entry in my pattern database is going to contain, or every entry in memory is going to contain exactly one value from my pattern database. And then I won't have any entries there that will be unused. And what's even more important is I won't have two states get the same entry here. I have two states in the real state space because of my abstraction will be mapping to the same location in memory. But that's fine because I've already decided to do that abstraction. But what I don't want to see, of course, is I wouldn't want to have like some values that were some entries that were the values weren't being used, and then somehow my pattern database mapped two states to the same value here. Okay, so this gives us permutations. It talks about the mixed radix representation. And then given that, there is an algorithm that allows us to do better than this. And so I'm going to just look, we're sitting at 30 minutes right now. So what I'm going to do is I'm going to end this video just for keeping it shorter. And I'm going to have a second video after this that is going to show both an O of n time algorithm for computing rankings. And then also I'm going to show when we're actually trying to do a pattern database where we're trying to rank a subset of a permutation, or also called a K permutation, then we have to do things just a little bit differently to get the numbers to actually work out properly. And so I will show that in the next video.